Welcome to part 2 of our discussion of interference, and here specifically we're going to be looking at double slit interference. If you haven't checked out part 1, you want to go ahead and do that so that you know what is going on here conceptually. So in this video we're going to show geometrically and mathematically how it's possible for this kind of interference pattern to occur. Now what I've done is I've constructed a kind of enlarged version of this part of the experiment. So I've the card with the two slits over here and the screen over here. And what I'm going to do is start labeling some values that are important. So between the two slits, this distance over here is going to be referred to as the distance d. Now what's really important here is to note that I'm only showing two individual light rays, one coming from each of the two slits. If you remember, there's little wavelets coming through here, and each wavelet is going to contribute to a light or dark spot that forms over here. Now what I'm going to tell you is that we're looking specifically at a light band or a light spot on the wall, just for the sake of this video. But we could be looking at a dark spot as well. Now the line that goes from the middle of the two slits all the way across is of length L, so that's the entire distance from the cards to the screen, and it's going to hit exactly where the central maximum hits. And the central maximum, remember, is a light spot. There's also an alternating dark spot on either side of it, and so on and so forth. Now we describe the light spots in numerical order. So this one would be what we refer to as m equals 1, just to represent a number for the first light spot. The first dark spot might be m equals 0.5, and the negative values would be below the central maximum. So what I've done here, as well as I've drawn an angle or a line in here that bisects the angle formed on the wall between the two rays that come from each of the wavelets that are propagating through the distances. And now we're going to talk about the primary reason for why the interference happens. So I've zoomed in over here, this portion over here, and you can see a little bit more closely what's happening. But before we get to that, we want to talk about what's known as path difference. This is one way of describing if waves will construct or destruct. So what I'm going to have here is the starting line, or the starting point, and I'm going to describe this or label this wave, wave 1, and this wave, wave 2. Now I'm going to say that wave 1 begins, and after some amount of distance, which I'm going to label as delta r, some books will label this delta L, and other values I use delta R, and this represents the path difference. Now the path difference is the distance between the start of wave 1 and the start of wave 2. And if wave 2 starts exactly when the second wavelength of wave 1 is starting, they will be completely in phase with one another. So this value delta R, if it's a distance that occurs in whole number integers of the wavelength, that would be described as producing constructive interference. So what we're going to do here is say that delta R is a distance, but it can be labeled in terms of the integer number of the wavelengths. Now you can see why these need to be monochromatic sources, because the wavelengths have to have the possibility of even matching up, whereas if they weren't, if one was more spread out than the other, they wouldn't be able to completely interfere or constructively interfere. So we would say, rather than describe this as just a set distance, we could say maybe 5 nanometers, we would instead say it's a multiple, it's maybe 17 wavelengths have occurred of wave 1 when wave 2 starts. And so you should hopefully be able to see that if m is a whole number integer, doesn't matter if it's even or odd, if it's a whole number integer, we'll have constructive interference. And if it is a half number integer, then we'll have destructive interference. So there will be the possibility of constructive or destructive interference no matter how many wavelengths of W1 have occurred before wave 2 begins, as long as it's a whole number variety. And so what we're going to look at here is, how do we get the path difference on this picture? Well, it's not as obvious at first glance. So I'm going to show you here that if I draw a perpendicular line to this bottom wave here, this distance over here is actually the path difference. Now, if you want to spend some time trying to figure out how that is the path difference, go for it. I'm not going to get into too much detail on that here just because of time for this video. Now, remember that this distance over here, which I'm going to sketch out in a different color, this distance over here, that's going to be D. That's the distance between the two sides, or between the two slits. And this angle over here happens to be the same as the angle over here. Now I'll show you which angle we're talking about. It's this angle between that bisecting line and the length, the distance between the two. And we are looking at particularly this tiny little angle over here, and those happen to be the same angle. And once again, I'm not going to be proving that in this video, but you can figure out for yourself just through some similar triangles how to get that value. Now what I'm going to write here is that the path difference, which is delta R, that's the difference between when one starts and the other one, where they would line up. So that's why it's a perpendicular line between the two. That distance right there, if it occurs in a whole number integer, then we'll have constructive interference. So let's go ahead and write something in terms of that angle. Well, I could say that the sine of that angle is equal to the path difference over the slit distance. And then if I solve for delta R, I get that is equal to d sine theta. So this is one version of an equation for path difference, and this is another version of an equation for path difference. Both of them are the same value, delta R. They can tell me that distance. Now what I'm going to do is go back to the large picture, and we're going to take a look at how this angle over here relates to this angle over here. Well, what I'm going to say is that this distance where we have the first light spot, I'm going to label that as y. Now you can have any number of y values up the edge of the screen here, okay, or down the screen as we see here, and that's going to be an actual physical distance. So it's labeled as light spot 1, but we could say that light spot 1 is, say, 5 centimeters from the central maximum. Okay, so what I'm going to write here is that the tangent of this little angle over here is equal to y over L. Now because the hypotenuse of this triangle is effectively the same as, say, the base of the triangle, this value over here is really, really tiny. So essentially at very small angles, what we could say happens is that the tangent of the angle is approximately the same as the sine of the angle. And you can check this out if you actually graph them. So if you were to graph the two values, you would see that the functions overlap for very small values of the angle, and then they'd start to deviate at a certain point. So this works for small angles. So because we know that this is true, what I can do is come back down to this idea over here and say that this sine theta is equivalent to this tangent theta. And so what I've got then at this point is to say that delta R is equal to d times tangent theta, which is equal to y over L. Now in addition to that, I can set this equation equal to this side of delta R, and so I would have m times lambda is equal to dy over L. And this combination of the two variations of path difference with the small angle approximation, this will tell me a lot of information geometrically about what I'm seeing. So let's talk about just really quickly as we wrap this video up, what each of these values could tell you. Well, if we were inside of some sort of a detecting device, this would be the inside chamber of the device, and I could put some light through here and say I wanted to figure out what light was being emitted, what wavelength of light is being emitted by a certain chemical. So in question here is lambda. Well, I could do a few different things. The L value is something that's programmed in because it's a fixed value here. In addition to that, we could say that we want to analyze it at this particular spot here, which is X amount of space away from the central maximum. And if this is a receptor plate or a detector plate over here, the detector would tell if that's a light spot or a dark spot. So if M is a whole number integer or not. And what it can do is then back calculate the wavelength by knowing the distance of the slits, how far up the screen in terms of meters or nanometers that the spot occurs, and then have to specifically put if it's a light or dark spot over the length of the total slit to screen distance, and I could calculate the wavelength. So this is a really cool way that can show you whether the waves will interfere constructively or destructively. But you see here, it's very important to distinguish that the wavelength of both must be the same, otherwise this doesn't even assist us anymore. So hopefully that helps. It does have a lot of details and assumptions in it, so pause and check out what you need to. And in the next video we're going to take a look at multi-slits. If I had more than two, and then also what if I only had one slit? Is it possible to get what we refer to as a diffraction pattern rather than an interference pattern in that circumstance?